Something passed through our solar system in 2017, and we still don't know what it was. It didn't behave like a comet. It didn't behave like an asteroid. It accelerated on its own, without any engine we could identify, without any gas trail we could detect, without following a single law of physics the way we expected it to. Every explanation scientists gave collapsed under scrutiny, and for years we had no real image of it, not one. We were theorizing about an object we had never actually seen. Until now. The James Webb Space Telescope changed everything. And what it revealed is only the beginning of a story that hasn't ended. There are moments in science when everything we thought we understood quietly breaks down. Not with a dramatic explosion, not with a public announcement, not with governments holding emergency press conferences, just quietly in the data, in a single measurement that refuses to cooperate with every model we have. October 19th, 2017 was one of those moments, and most people on Earth had absolutely no idea. A telescope in Hawaii, the Pan-STARRS. One survey telescope built specifically to scan the sky for anything moving, anything unusual, anything that shouldn't be there, picked up a faint signal. An object, moving fast, moving very fast, moving faster than anything that belongs to our solar system. Astronomers ran the numbers once, then they ran them again, then they called in colleagues, then those colleagues called in more colleagues. Because what the data was suggesting was something that had, up until that moment, existed only in theory. This object had come from outside, from beyond the sun, from the space between stars. It was the first interstellar object ever confirmed to have entered our solar system in recorded history. They named it Oumuamua. In Hawaiian, it means first messenger from afar, or more precisely, a scout sent ahead. And the name, as it turned out, was far more appropriate than anyone realized at the time. Think about what that means for just a moment. In all of recorded human history, in all the centuries of astronomy, in all the decades of modern telescopes scanning the cosmos, we had never once caught an object from another star system passing through our neighborhood. Never. And suddenly, here it was. A visitor from interstellar space, moving through the inner solar system at roughly 26 kilometers per second, relative to the sun. That's not a typo, 26 kilometers per second. By the time you finished reading that sentence, Oumuamua had already traveled hundreds of kilometers further away from us. Here's the first problem. By the time we discovered it, it had already made its closest approach to the sun. It had already passed by. It was already leaving. Astronomers had a window, a narrow, rapidly closing window, to observe this object before it vanished forever into the darkness between stars, never to return. And so every major telescope on Earth and in orbit pivoted toward this tiny, fading point of light racing across the sky. What they measured in those weeks changed astronomy permanently. First, the shape. Every method of measuring Oumuamua's brightness showed the same extraordinary thing. The object was tumbling, and as it tumbled, its brightness varied dramatically. Not by a small amount, not by the kind of variation you'd expect from a lumpy rock spinning in space. The brightness varied by a factor of 10. That is an almost impossible number. For an object to dim by a factor of 10 and then brighten again as it rotates, its shape would have to be radically elongated. The models that fit the data best suggested an object somewhere around 10 times longer than it was wide. Imagine something roughly 400 meters long and perhaps 40 meters wide. A cosmic cigar, a needle thrown across the galaxy. Nothing in our solar system looks like that. Nothing. Every asteroid, every comet nucleus, every small body we have ever observed, none of them have that kind of extreme elongation. Some scientists later suggested it might be more pancake-like than cigar-shaped, but either way, the geometry was unlike anything we had cataloged before. But here's where it gets worse, or more interesting, depending on your tolerance for having your understanding of physics quietly dismantled. As astronomers tracked Oumuamua's trajectory, something strange emerged from the orbital calculations, something that wasn't supposed to be there. The object was not following the path that gravity alone would predict. It was being pushed, gently, but measurably, undeniably pushed in a direction away from the sun. A force was acting on it beyond gravity. In comets, this is common. When a comet gets close to the sun, ice on its surface sublimates, releases gas, and that outgassing creates a small rocket effect that nudges the comet off its purely gravitational path. That's normal. That's expected. Scientists see it all the time. But Oumuamua showed no signs of outgassing. None. No dust cloud, no coma, no tail, no detectable gas emissions whatsoever. Observers pointed some of the most sensitive instruments in the world at it and found nothing, and yet the force was real. The excess acceleration was measured at a statistical significance of 30 sigma. In science, 3 sigma is considered significant. 5 sigma is essentially certain. 30 sigma means the probability of this being a statistical error is so vanishingly small, it becomes meaningless to calculate. Something was pushing Oumuamua, and we could not see what. And this is where everything changes. Because at that point, the scientific community splintered. Some researchers proposed it was a new type of object, a dark comet, one that outgasses molecular hydrogen, a gas so light and transparent that our instruments simply couldn't detect it. Hydrogen outgassing would be invisible, yet would still produce the acceleration we observed. In 2023, researchers at Berkeley published exactly this argument, and it gained significant traction. Others proposed Oumuamua was a fragment of frozen nitrogen, shaved off the surface of a Pluto-like world in another star system, a flat pancake of exotic ice that would be pushed by solar radiation pressure like a very thin sail. Still others proposed, and this is the theory that set the internet on fire, that Oumuamua might be artificial, a probe, a thin solar sail deliberately constructed drifting through the galaxy. Harvard astrophysicist Avi Loeb published a paper, and later an entire book, arguing that this possibility could not be dismissed on scientific grounds. Read that again slowly. A tenured professor at Harvard, one of the most credentialed astronomers in the world, published a peer-reviewed paper arguing that we could not rule out the possibility that Oumuamua was built by somebody. Now, the mainstream scientific community pushed back hard on that interpretation. And there are good reasons for skepticism. Extraordinary claims require extraordinary evidence. And the hydrogen outgassing explanation fits the data without requiring any assumptions about extraterrestrial intelligence. But what everyone agrees on, what no one disputes, is that Oumuamua was anomalous. Genuinely, profoundly, historically anomalous. It broke every template we had for interstellar objects. And here was the cruelest twist of all. We never got a clear picture of it. By the time the world's scientific community fully mobilized to study this object, it was already fading. The Hubble Space Telescope tried. The Spitzer Space Telescope tried. Ground-based observatories across multiple continents tried. Now, what they produced were blurry point sources, indistinct smears of light against the dark, not images, but suggestions of an image. The official NASA page for Oumuamua shows an artist's impression, a beautiful, detailed rendering of a tumbling red cigar in space, because no telescope on Earth or in orbit was capable of producing an actual photograph of the thing. We were analyzing a ghost, building entire theoretical frameworks around an object we had never truly seen. That is the context that makes what happened next so significant. The James Webb Space Telescope was launched on December 25, 2021, from the Guiana Space Center in French Guiana. It carried with it a 6.5-meter primary mirror, a sun shield the size of a tennis court, and the most sensitive infrared instruments ever, deployed in space. The engineering behind Webb is almost incomprehensibly ambitious. The mirror itself is made of 18 hexagonal beryllium segments coated in gold, because gold reflects infrared light with extraordinary efficiency. To reach the operational sensitivity it needs, the telescope must operate at temperatures close to minus 233 degrees Celsius, just 40 degrees, above absolute zero, the coldest temperature that physics allows. Webb sees the universe not in visible light, but in heat, in the glow of infrared radiation that invisible human eyes cannot process. Radiation that carries information across distances and through dust clouds that would be completely opaque to ordinary telescopes. Webb was designed, among other things, to look back to the very first galaxies, to find planets orbiting other stars, to analyze the atmospheres of worlds light years away. But scientists had also quietly hoped it might, under the right circumstances, do something else, something more immediate, something closer to home. They hoped that if another interstellar visitor came through our solar system, and models suggested they should be passing through relatively frequently, perhaps once per year in the inner solar system, Webb might be positioned to study it in a way no previous instrument could match. What most people are not seeing is this. The real story of Webb and interstellar objects is not just about Oumuamua. It's about what happened next. And what happened next arrived faster than anyone predicted. On July 1st, 2025, less than 8 years after Oumuamua's discovery, the Atlas Survey Telescope in Chile detected another interstellar interloper. This one was designated 3I Atlas, the third confirmed interstellar object ever discovered in our solar system. And the contrast with Oumuamua could not have been more dramatic. Where Oumuamua was small, mysterious, and already departing when found, 3I Atlas was discovered on its way in. Scientists had months to watch it approach, study it, prepare for its closest encounter with the sun. Where Oumuamua left us with almost no images, 3I Atlas became one of the most intensively observed objects in the history of astronomy. And Webb got there first. On August 6, 2025, the James Webb Space Telescope turned its infrared instruments toward 3I Atlas and collected its first data. What came back stunned researchers. The spectral analysis revealed the chemical fingerprint of the object's surface and coma in extraordinary detail: water ice, carbon dioxide, and something unexpected: methane. Methane outgassing from an interstellar comet raised immediate and profound questions about the temperature environment in which this object formed. Methane freezes and stays solid only at extreme cold, far colder than the outer regions of our own solar system. The presence of methane pointed to origins in an environment far more frigid and remote than astronomers had modeled in their early predictions. This thing had formed somewhere deeply, profoundly cold, beyond the orbit of its parent star's most distant frozen worlds, and had been traveling through the darkness of interstellar space for so long that the cosmic environment had left its chemical signature baked into its composition like a time capsule from another epoch of the universe. According to informed sources in the scientific community, the Webb data on 3I Atlas represents the most detailed compositional analysis ever obtained for a body originating outside our solar system. Every molecule detected is a message, a word in a language being slowly decoded, and the message keeps getting stranger. Consider the size. Oumuamua was estimated to be no more than 200 meters in its longest dimension, a tiny fragment of whatever larger body it came from. 2I Borisov, the second interstellar visitor discovered in 2019, was roughly 700 meters across. 3IR Atlas, as measured by the Hubble Space Telescope in post-perihelion observations from December 2025 through January 2026, has an effective nuclear diameter of approximately 2.6 kilometers. That makes it at least 20,000 times more massive than Oumuamua. And yet, it arrived with a velocity at infinity of approximately 58 kilometers per second, even faster than Oumuamua's already extraordinary speed. Think about the energy required to accelerate a 2.6 kilometer rock to 58 kilometers per second and hurl it across the void between star systems. Whatever gravitational interaction ejected this object from its birth system must have been catastrophic. A close encounter with a massive planet, a stellar flyby, an event violent enough to tear this multi-kilometer body free from the gravity of its parent star and send it drifting across the galaxy for what scientists estimate could be billions of years. Billions, not millions. Billions of years, moving through the dark between stars, absorbing cosmic rays, building up a thick reddish irradiation crust on its outer surface, carrying frozen within it the chemical record of the planetary system where it was born, a system we may never be able to identify, orbiting a star that may no longer exist. But here's where it gets worse. Or, more precisely, here's where the implications begin to stack in ways that become genuinely difficult to process. The discovery of 3I Atlas, combined with the refined theoretical models that emerged from analyzing Oumuamua and 2I Borisov, now suggests that our solar system is being traversed by interstellar objects far more frequently than previously understood. Current estimates, based on the detection rate of these three objects and correcting for the observational limitations of our telescopes, suggest that at any given moment there may be thousands of interstellar objects larger than 100 meters passing through the inner solar system. Thousands, drifting through undetected, invisible to instruments not sensitive enough to catch them, passing through our neighborhood of space between the planets and departing back into the dark without leaving any trace we're capable of measuring. We live in a solar system that is, in a meaningful sense, constantly being visited by debris from other star systems, fragments of worlds that formed around other suns, remnants of cosmic events that happened in neighborhoods of the Milky Way we have never seen and cannot name. What most people are not seeing is the full philosophical weight of that. This isn't just an astronomical curiosity. This is the universe telling us something fundamental about the interconnectedness of planetary systems, about the movement of matter across stellar distances, about the possibility that the building blocks of life, the organic molecules, the amino acid precursors, the carbon compounds, might travel between star systems aboard exactly these kinds of wandering bodies. And now, for the first time in history, we have an instrument sensitive enough to actually read what these objects are carrying. The James Webb Space Telescope does not just take pictures. It performs spectroscopy, the precise measurement of which wavelengths of infrared light an object absorbs or emits. Every chemical compound has a unique spectral signature, a fingerprint in light that identifies it as distinctly as DNA identifies a living organism. When Webb pointed its instruments at 3I Atlas and measured its spectrum, it was essentially reading the chemistry of another star system. The water ice on that comet did not form in our solar system. The carbon dioxide trapped within it did not condense around our sun. The methane frozen into its nucleus formed in conditions that existed around another star, in a protoplanetary disk that assembled billions of years before the Earth existed. And now that chemistry is here, passing through, being measured, being understood for the first time, this is not chaos. This is the universe being legible for the first time to instruments we have only just built. But let's return to Oumuamua itself, because the story there has not ended. It has only deepened. The question of its non-gravitational acceleration has now been partially, not fully, resolved by the dark comet hypothesis. In 2024, astronomers identified 14 small near-Earth asteroids that exhibit the same kind of anomalous acceleration Oumuamua showed, pushing away from the Sun without any visible cometary activity. These 14 objects now form a newly recognized category called dark comets, bodies that outguess volatile compounds in ways that are effectively invisible to current observational methods. Oumuamua, under this framework, would be the first and most dramatic member of this new class. Not an alien artifact, not a fragment of exotic nitrogen ice, a comet that simply doesn't look like a comet because the gas it releases is hydrogen, the most abundant element in the universe, and also one of the hardest for our instruments to detect in this context. That explanation satisfies many scientists, but not all. And the honest assessment, the one that doesn't reach for comfort before the evidence demands it, is that we still cannot say with certainty what Oumuamua was made of, where exactly it came from, or what mechanism produced its specific pattern of non-gravitational acceleration. The data points toward the dark comet model, but the data does not close the door on other explanations. And in science, open doors have a way of leading somewhere unexpected. According to some researchers studying the geometry of Oumuamua's acceleration, the push it received was remarkably consistent. Not erratic, not rotating with the tumbling of the object, but directed steadily away from the Sun in a way that several papers have described as unusually clean. That cleanliness is what keeps certain scientists returning to the solar sail hypothesis, not because they believe it, but because the alternative explanations have not yet perfectly reproduced the observed data in every detail. And this brings us back to Webb. Because the real strategic importance of what the James Webb Space Telescope is doing, the layer of this story that most coverage misses, is not just about imaging specific objects. It is about establishing, for the first time in history, a baseline of what interstellar material looks like. Every spectrum Webb captures of 3I's atlas, every measurement of its chemical composition, every comparison between what we detect and what we would expect from different formation environments builds a library, a reference database of interstellar chemistry. And that library will matter enormously when the next interstellar object arrives, and the one after that. Because what the discovery of 3 interstellar visitors in less than 8 years tells us is that this is not a rare phenomenon. This is a regular feature of our solar system's environment. We simply lacked the instruments to see it before. Now we have those instruments, and they are working. Consider what Webb's infrared sensitivity means in practical terms. Visible light telescopes like Hubble are fundamentally limited in what they can detect about the composition of cold, distant objects. Infrared telescopes, by contrast, can detect the thermal emission and the absorption features of molecular compounds that are invisible at other wavelengths. When 3I, our atlas, passed through our solar system at its closest approach to the Sun on October 29, 2025, Webb was already collecting data. The methane detection was itself remarkable. Methane's spectral signature in the mid-infrared is distinctive, and the fact that it was present in measurable quantities confirmed that this object had spent its long interstellar journey in temperatures cold enough to preserve it. The leading interpretation among scientists is that 3I Atlas began its journey in the outer regions of its parent star system, possibly in an Oort cloud analog, a distant reservoir of icy bodies that most stars are thought to possess, and was ejected into interstellar space through some gravitational disturbance, possibly billions of years ago, possibly during a period of planetary rearrangement similar to what astronomers believe happened in our own solar system's early history. The universe, in other words, ejects its debris. Every star system with planets is probably throwing material out into interstellar space. And some of that material, a vanishingly small fraction but not zero, eventually drifts close enough to another star to become detectable. We are, in a very literal sense, sampling the wreckage of other solar systems, reading their chemistry in the infrared glow of objects that have spent longer in the dark between stars than our own sun has existed. The real story is that Webb has not just given us images, it has given us a new discipline. Interstellar object science, the systematic study of visitors from other star systems, barely existed as a field before 2017. Now it has 3 objects to analyze, a dedicated community of researchers, multiple active space telescopes gathering data, and a rapidly expanding theoretical framework. Within the next decade, as ground-based survey telescopes grow more powerful and Webb continues operations, scientists expect to detect interstellar objects with enough advance notice to potentially intercept them, not land on them, not yet, but fly past them, deploying instruments, measuring their properties in situ, sampling the actual material of another star system with instruments that travel from our own. The European Space Agency has studied mission concepts for exactly this. The window of opportunity is tight every time. Interstellar objects move too fast, arrive without notice, and depart too quickly. But the ambition is real, and the engineering is being developed. What that would mean is almost too large to fully absorb, to physically reach an object that formed around another star, to bring its chemistry into contact with instruments built on Earth, to close, in some small but measurable way, the gap between our solar system and the vast network of stellar systems scattered across our galaxy. Every star you can see on a clear night is a sun. Most of them have planets. Some of those planets may have oceans, atmospheres, perhaps chemistry more complex than anything we have ever imagined. And some of that chemistry may already be here, frozen into the nucleus of objects like 3I Atlas or Oumuamua, drifting through our neighborhood, waiting to be read by the right instrument. We are building those instruments. We are finding those objects. We are, for the first time in human history, actually beginning to decode what the universe has been trying to hand us. But here is what remains unresolved. Here is what keeps scientists awake. Not in the metaphorical sense, but in the literal conference room, heated debate, staring at residuals at midnight sense. Oumuamua's behavior still does not fit any single clean model perfectly. The dark comet hypothesis explains the acceleration, but the expected outgassing signature is not definitively observed. The nitrogen ice hypothesis explains the shape and the acceleration, but producing that much nitrogen ice in a planetary system and ejecting it into space requires conditions that are statistically almost impossible. The solar sail hypothesis explains the acceleration and the shape, but requires abandoning the assumption that Oumuamua is natural, an assumption most scientists are deeply reluctant to release without far more compelling evidence. What we can say with confidence is this: Oumuamua was the first messenger. 3I Atlas is the second chapter. And whatever comes next through our solar system, and something will come, the mathematics of interstellar object flux guarantees it, will be observed with instruments and understanding that didn't exist 8 years ago. The story of humanity's relationship with interstellar visitors is not closing. It is opening. It is just beginning to reveal itself. And every answer Webb delivers seems to carry within it 3 more questions that nobody has yet thought to ask. Something passed through our solar system in 2017. We still don't know exactly what it was. A new visitor arrived in 2025, and Webb is still processing what it found. The universe is sending things our way: fragments, messengers, debris from distant worlds, or perhaps something stranger still. And we are only now, for the first time, sophisticated enough to begin reading the language they carry. What happens when we understand it? What are they carrying? And what exactly is the universe trying to tell us?